can hear you, but
Okay, sir.
I think you cannot hear me.
Yes, sir, we are audible to you. We are hearing you. Okay.
You hear me?
Yes, sir, yes.
Okay, good.
Okay.
So, yeah, please give some introduction for me.
Okay, sir. So, Dr. Yongpak Lee, sir, will be delivering the next lecture by online mode on metamaterial absorbers with multi-broad tailored band and perfect performance. To introduce him, I request Mr. D.P. Shinde, sir, to introduce Dr. Lee, sir.
Okay. Well, can I?
No, just 1 minute, sir.
Okay.
Good morning to one and all present here. Today we have gathered for today's international conference on smart materials for sustainable development, energy and environmental application under the aegis of RUSA Component 8, jointly organized by Department of Physics, Chemistry and Electronics in collaboration with IQAC and Student Teacher Research Cell. I feel extremely honored to introduce today's resource person, Professor Dr. Young Pak Lee. He is a professor of physics, Hanang University, Korea, and also professor of physics, optical science and engineering, Fudan University, China. Professor Dr. Young Pak Lee received his BS degree from Seoul National University, Seoul, South Korea in 1975 and the PhD degree in experimental condensed matter physics from Iowa State University, Ames, USA in 1987. His research has involved study of magneto-optical, that is magnetic, optical and transport properties, electronic structure of thin film and nanostructures. Also, characterization of surface and interface of thin film, including multilayers and so on. He has published 737 essay articles with an H index of 64 as of August 2021. Dr. Lee sir has global collaboration network 43 organizations in 16 countries and also organization of numerous international conferences and symposia and 265 international plenary talks. His current investigation include metamaterials, magnetic photonic crystal. Dr. Lee sir received 53 awards including award by Korean Minister of Science and Technology in 1992, also awarding as outstanding professor in research by Hanang University in 2012. He got Sunbong Physics Award, which is highest level award by the Korean Physical Society in 2014. He got Korean National Order of Science and Technology merit in 2017. Also got award of Best Advisor for Physics Thesis in 2017 in Korea by the Korean Academy of Science and Technology, the Korean Association of University. Actually, the biodata of Dr. Lee sir is very huge. I can short list in small para. Thank you so much for giving me opportunity to introduce such a great personality. Thank you one and all.
Thank you for excellent introduction on me. Okay, can I start now, right?
Yes, sir.
Okay, thank you. As I show you here, anyway, very happy to give us this keynote talk at this very special international conference. I should be there, but many foreign trip these days. So please forgive me. And I also thank organizer and many old friends there, including Professor Poa. Professor Poa is there? Yes. Okay, yeah. Hi. Okay. And my excellent former students there. Okay. So I'm proud of them. And then I really hope to be there. I meet you face to face. Okay, sooner or later. Okay, I'm talking about the metamaterial observer as far as time is allowed. Okay, so my affiliation and co-authors here. Okay. This kind of the three-layer structure is very typical for the metamaterial puppet observer, which was suggested in 2008, only not very long ago. Okay, and at the similar time, I also started to this kind of research. Okay, kind of one of the world frontier something in this field. The three-layer structure, the function of the three-layer structure is like this. The first one, top one, front one is so-called meta pattern layer, which let all the incoming the electromagnetic wave enter the system. That is the role of this meta pattern layer. So all the incoming electromagnetic wave entered into the system, and then the second layer is a so-called dielectric layer, which is store and dissipate the entered electromagnetic wave. Okay. The last one is not clearly seen here. This one is the same one. This is the thin. Here is rather thick, but usually very thin and continuous metallic layer, which is let entered electromagnetic wave not to go up. So in that way, we can achieve some perfect absorption. Okay, using this kind of three-layer structure. So since then, okay, so many patterns like that, and then like this, so many patterns is still going on. It's suggested, depending on the application frequency, operating frequency and application. Okay, so many of the pattern is actually contributed by my group. Okay. So, and then there are so many some principles in designing this metamaterial puppet observer. But one of them is, for example, this is this is we call unicell. The size of the unicell is nearly inversely proportional to the frequency. And then another important one is we need some resistant element in the system to have some broad spectrum. Okay, and many others, but I don't have to introduce everything here. But the two principles is work very much in my presentation. My kind of the recognition, my recognition in this field is the very famous journal in the field of electromagnetic wave and application asked me to write some kind of first review paper in this field in 2014 something, and it's published here. It's a really long 50-page invited review paper. Still, it's have a played as a kind of textbook, and I think it's still going on. And then in 2017, I asked to write another review paper on the flexible perfect metamaterial observer, which is also very important even these days. In 2007, so you can get if you need more information, you can get this paper. It's open access, I think. And then 2020, I asked again to revise this first invited review paper to update this all the knowledge. So that was also published in 2020. It's also a long review paper, updated long review paper, so you can get it. And then lastly, the same year, I was asked to write some emphasizing low frequency application. So it's also very important. So that also available to you, I think. And in addition to the invited review paper, I also asked to write the textbook for the people, asked by the Spring Nature. So that title is shown here. So actually asked in 2015, and I was released in 2016. Okay, it's still very popular, and it's kind of a textbook in this field, classical textbook. So I'm very happy to have this textbook. And then at similar time, I also appointed as editor in the applied physics field by the Spring Nature company. Okay, that position is still going on. So then the aim, continued aim from the beginning of this multi-material absorber is these four aspects. For example, we pursue polarization independence. P, TM doesn't matter, okay? And then why we should better cover the wide angle of distance up to 45, many big angle, okay, to be more practical. And then also, depending on the application, we sometimes need a single frequency, and but usually multi or a broadband might be useful. I'm emphasizing this application this time, okay, because I cannot cover everything. And then also we can, depending on the application, we need many frequency range. We should cover the many frequency range, okay, at the same time or the separately. And then it's even though it's suggested only 2008, already some of them is being commercialized. Okay, it's almost in the application of the metallurgy. Okay, so I'm also doing some kind of the application, the commercialization of some of them. It's this kind of item recently, together with some relevant Korean company. So these days I'm doing both the basic research and also kind of the application, beyond the application, some commercialization research too. So now some basic result for the broadband application. Okay. As I told you, to have the broadband property, we better have I told you here, we better have some resistant element in the system. Okay, but we have 3 layers, so we have 3 cases to include the resistant layer, because this layer or this layer and the bottom layer. Okay, 3 cases and their combination. Okay, so let me. The first one is posted here, so we can get more information there. And first of all, we replaced the last bottom thin, continuous metallic layer with some low conductive layer, which has some resistive element. Okay, it has some conductivity, means not perfect conducting, right? So in that way, we give some resistant element in the system. Okay, like that. Then before that low conductive layer, we could only this kind of the separate P. Okay, this is fundamental, so forth, and this is fifth harmonic, fifth order P. Okay, it's separate like that. But after replacing with this low conductive layer, these peaks is merged and enhanced to be this high and broad. Okay, and in other words, absorption over 90% is obtained, a very wide band. For example, from 0.2 to 3.8 gigahertz. I'm dealing with the microwave, the application now. Okay. So in this kind of system, most important parameter is conductivity of this low conductivity layer. Okay. So we could optimize this parameter, the conductivity of the low conductivity layer, by doing this one. Absorption versus frequency versus conductivity. Okay. Then we could get the most broad case can be obtained at the conductivity of 0.02 Siemens per meter, something like that. Okay, in this case. So we optimize the conductivity like that way for the broadest user. Then also, okay, so that is for first case for us to give some resistive element in the mathematical observer system. And then, because of time, let me go into the second case. The second case is also is published here. Recently, this journal is grown to be very high in effect now. It's published by Japan. And we put the resistive element on the meta pattern layer, top layer here. So we put the resistive element here. Okay, in the second case. Okay. So to do that, we design this kind of scheme. Okay. Well, first of all, we need we put the rectangular copper patch with different size. Why we put this one? To have the broadband, first of all we need some kind of many small absorption peak before introducing resistive element in the system. So these rectangular copper patch with different size is very important. Each size gives one frequency. Okay, so in that way we could have some many small peaks like this. Okay, and then we connect those metallic patches with some conductive layer, conductive fiber which give the system give the flexibility and resistance to the system. Okay, both. Because we finally we want to have some flexible metal material observer. Okay, so we consider that. So we try to use conductive fiber, which give both property. Okay, then after putting this connecting with some conductive fiber, the spectrum is enormously is enhanced and sort of merged between the peaks. So it comes to be like that. Okay, surprisingly. So before the connection with the conductive layer, this observer is just to show this 5 peak, small 5 peak at 0.95, 1.7 to 2.0, 4.4, and 5.49, something like that. And then after connection, it comes to be over 97%. But even we recall over 90 or 94%, we call the perfect. Okay, so it's over 97% in the range of 0.97 to 6.12 gigahertz, very low. Okay, so that is the way we could get another way to get the broadband spectrum in the system, of the system. And then then, as I told you, to want to be broad, the most, in three-layer structure, the most thick part is, dielectric layer, usually. So, usually, the common application, we use a very cheap and hard FR4 plastic. But if we replace this one with the polyimide, flexible polyimide, then the system can be bent, flexible like that, okay? You can see there's some catch and some connection with conductive fiber here. So it can be bent like that, even this status. Okay. Then the another important thing is for this flexible system, the property should be maintained even after it's bent. Okay. So we could check the angular dependence of the property up to 60 degree is nearly unchanged, which means another way, which means also at the same time, then the property, absorption property is maintained even when this metamaterial coupled absorber is bent. Okay, bent this much. Okay. So we could get some flexible and very broadband metamaterial coupled absorber in this way. The third case is we put this resistor layer, resistor element. Now is the last layer might be the dielectric layer. Okay, so we put some dielectric resistor layer inside the dielectric layer like that. Okay, like that. That is the second case, the third case, I think. And then the pattern is the similar to here. We design some the different size pattern, which gives many small absorption peaks. Okay, like this pattern. And then we just combine this resistor layer in the dielectric layer. So we could get the small peaks is merged and nest like before. Then we could have this very broad and very high absorption peak spectrum like that. That is also this published here, so you can train it. So that is this way. The three cases is the three ways to get the broadband using this metamaterial coupled absorber. Okay. But recently also not the broadband, but sometimes you need some medium band application. Okay, tailored medium band application. So for that kind of application, how we can do that? It's very simple, but actually not very simple, but the idea is very simple. We might use this system, but this pattern gives many small peaks, right? Instead, okay, we don't need not many small peaks, right? So we may adopt some the pattern to give some one sharp peak, something like that. Okay, and then this pattern, and combined with the resistor layer here, we could control the bandwidth. Okay, as you want. Okay. So this the very one sharp peak, the pattern will give peak is usually known as extraordinary optical transmission. The pattern. Okay, like this. Okay. So using this kind of idea, we design some application we want to have this medium band, not very broad, okay, from 5.55 to 6.05 gigahertz. But we want to have very high absorption, and in this band, over 90%. Okay, and then also we want to have some, at the same time, we want to have some, the angular instant angle independence. For example, even up to 45 degree, the absorption is don't go down less than 97%, something like that. They're very high, okay, even at 45 degree. And then also we want to have some polarization independence like that. No change between T polarization and TM polarization, something like that. With this kind of requirement, to satisfy this kind of requirement, we design this kind of it's deviated from this conventional EOT pattern. So, but in principle, the same similar actually the property. Okay, and then also to have a angular, instant angle independence and polarization independence. We better have some symmetric pattern. Okay, it's like that. So this pattern and it's kind of optimization, and together with this register layer in the dielectric layer, we could get a very high absorption in this medium range of bandwidth. Also polarization independence, as I told you, and also the angle of instant independence. Okay, but the only not very broad, only the bandwidth we want to have. Okay, so-called tailored medium bandwidth. And then the power over this the metallurgical design is, as I told you, if we change the unit cell size, then we can change the operating frequency without changing much. Okay, so usually basically same pattern, but just reduce the size. Then appropriately, then we could get the same property, similar property, even at the 10 gigahertz application. Okay, so it can be continued for the different frequency. But that is a power. The first principle I mentioned together with the 3A structure. Okay. And then some more analysis on this structure by doing the power loss density on the surface of this polyimide. The dielectric layer is it want to be a flexible polyimide, okay, to be flexible. So this layer and also the resistor layer. Okay, then we found a dielectric loss. There are two kind of loss in the metallurgical particle observer. It's dielectric loss and ohmic loss, sometimes a combination. Okay, so both dielectric layer, dielectric loss, and ohmic loss here is co-exist in the system. And then but the most is the bright reddish one is most energy is consumed. So most loss of energy concentrated on the end of the two bars at the top. Okay, since these two bars act as an antenna, as you can imagine. And then we could control the bandwidth. The bandwidth of the absorption is really depends on the concentration of the electromagnetic field, which means more divergent of electromagnetic field like this. Okay, then the wider the absorption bandwidth. So in that way, we could control the bandwidth as you wish. Okay, so that is one way to have one way we develop. Okay, for the medium, tailored medium bandwidth using the broadband, the structure we already had. And yeah, well, I was so these days, this very property is very good, but thinking about some kind of commercialization and fabrication, we found this fabrication of this resistor layer sometimes it's bother us. Okay, so instead we develop some more practical design. For example, instead of this register layer, we put very small number of register at the meta pattern, layer. For example, this is one unicell, but instead of putting the register layer here, we put a small, really common register here. Each one or two in unicell. Okay, so it's more convenient in fabrication for than the register layer inside the product layer. So yeah, we already, it's not done yet, but we already got some very broadband things, okay, considering the easier fabrication. But furthermore, these days we think about we might not have some register, okay, in the system. Okay, instead we by some interaction of the pattern. Okay, we might create some register-like property in the pattern. So in that way, we could get some without register. We could get some broadband metamaterial puppet observer. Okay, this is kind of course, world first investigation. Okay, so for example, this is not final yet, so no register at all. But just using the interaction of the pattern, we might have some very broadband spectrum like that. Okay, then depending on how complicated the pattern, may be much better for the commercialization and fabrication and commercialization. Okay, so that is also we try to if the broadband is achieved, then we might move towards some flexible and tailored band using this two-dimensional structure without register. Okay, depending on the progress. Okay, so that is kind of the recent progress on the broadband and the medium tailored medium band metamaterial puppet observer. Okay, the whole application of the metamaterial here, the metamaterial puppet observer only belong to here, study of the control of the electromagnetic response and its spatial distribution and dispersion. Okay, this field is already, is pretty much, flourished, and even some of them are even commercialized. Okay? The first in metamaterial, but not all in metamaterial. The field. That's not all. There are so many other applications and research. So, which means it's very bright field, still very bright field for metamaterial. Bright future. Okay. Okay, so that's kind of wrap up my talk. Let me just add my joke. Okay. Recently, I'm also writing novel. Okay, not only physics. So only one guy in Korea doing physics and writing novel together. Okay, I'm the member of the Korea Writer Association and also Korea Novelist Association. Okay, I wrote 5 long story novels already, and also 3 long story novels. The 3 of the 5 long story novels already translated into Chinese. So I look forward to some translation in Indian language. Okay. In the two of this novel is belong to one saga novel. So I'm writing the third part of this saga novel these days. Okay. Thank you very much.
Thank you very much, sir. Any questions from the audience?
Hello, Professor Lee. Hello.
Hello?
How are you, sir? I'm Professor Pawar here, meeting.
Okay, how are you? How is it?
After a long time, so very nice, very nice to listen you. First of all, let me congratulate.
It's not clear.
Yeah. Okay. You have made a very nice presentation and good results. What is a status of translational research of your outcome?
What,
So, okay, it's a very interesting work.
I cannot hear you. Your voice is
Yeah. Okay. So, it's a very interesting work. So, do you have any plan of translational research?
sorry, actually, I could not catch your question, okay? Because I say voice is, interrupted, okay?
Okay.
Frequently.
It's okay, sir. Thank you.
Okay, now I request Dr. S.G. Chavan, sir, to give the vote of thanks for this session.
Good afternoon to all of you. Department of Physics, Chemistry and Electronics organized two-day international conference on smart material for sustainable development, energy and environmental application. On the behalf of the Department of Physics, Chemistry and Electronics and Karmavir Bhaurao Patil Mahavidyalaya, Pandharpur, I take this opportunity to propose the vote of thanks those who have directly and indirectly involved this international conference. First of all, I thanks to today's speaker, Professor Dr. Young Park Lee from Hayang University, Seoul, South Korea. Sir, your talk based on metamaterials, fabrication process and their applications in bandwidth were really enlightening with your knowledge and virtually presence. I would like to thank our college principal, Professor C.J. Khilari sir, for this valuable guidance for every time. I special thanks for organizing committee, teaching, non-teaching staff for their constant supports. I thanks to I thanks to inaugural respected members, Pawar sir, M.M. Salunke madam, from the behalf of the Department of Physics, Chemistry, Electronics and KBP Mahavidyalaya, Pandharpur. Especially, last but not least, I thanks to all the participants from the various university colleges coming here and actively participate this international conference. Thank you one and all.
Thank you.
ये